Good morning, everyone, and welcome to this special talk. We are celebrating the World Environment Day. It was actually yesterday, June 5th, but since that was a Sunday, we are celebrating it today. In fact, this whole week we'll be conducting some more events for that. And as all of you know, this talk is being beamed live on WebEx and also on YouTube. So let me introduce the speaker today. So Professor A.P. Dimri, he is the director of Indian Institute of Geomagnetism at Mumbai presently, and he is a faculty member at the Jawaharlal Nehru University Physics Department. So his areas of interest and specialization are regional climate modeling, climate dynamics and variability, and climate change. And he has had more than 2 decades of experience as research as a scientist in DRDO, and then he joined JNU in January 2008, and then he's continuing there. And he has received several awards and honors for his work. For example, he is a fellow of the Japanese Society for the Promotion of Science, JSPS. He was also a junior associate at the ICTP in Trieste. He is also a fellow of the Indian Geophysical Union, and he has received a technology award from the DRDO, Government of India. He's also received a Siachen Medal from the Ministry of Defense, Government of India, and so on. And he's a member of several organizations in India and internationally. So he is. We are very happy that he is here with us today, offline, and this is one of the first offline talks that we are having after a very long time. So it's a pleasure to welcome you, Professor Dimri. And today he is going to talk to us about climate change and extremes over the Himalayas. So welcome.
Good morning to all. Thank you, Professor Buddhiraja, for bringing me to JNC and interacting on the subject. Primarily, basically, I'm also a physicist, but I moved to atmospheric physics and see how the atmosphere behaves. And when I say atmosphere, again, it is the lowermost layer of the atmosphere, which we call in atmospheric science troposphere. And recently, I moved to geomagnetism, where we are kind of looking at more larger scale. And then here I am only presenting work which is at the lower troposphere, and very oftenly I'll use this word as an atmosphere. Well, Environment Day is there, so briefly to tell me, Environmental Day was kind of UNEP wanted that, WMO wanted that decades back, that what Environmental Day is important for. In general, we all have that environmental concern, be it water, be it air. And then if you see, I was discussing with Professor Buddhiraja that some of part of JNC is getting flooded, and hence you have urban planning issues also. And this problem is happening everywhere, not only here. Delhi is getting flooded, Mumbai is getting flooded. It was meant for 100 people, and there almost 1,000 people have come to live in. Now, Delhi has the worst problem is that the blueprint of the under sewage line is not there. So now the issue is that where the water will go, the water which is meant to exit for 100 people, now that 1,000 people, water is exiting from the plant. So now their new concept of urban planning is coming. New point of urban jungles are coming because you have a skyscraper. If you look around 20 years back, you will see the satellite imageries and you see it now. You will find that land use, land cover planning is completely changed, and by virtue of you all are the physicists, there will be coupling of the land surface with the adjacent atmosphere, and that coupling, when you are looking at, that is bringing a lot of changes. And that's where the context of global warming, that's where the context of emissions, that's where the context of the climate change is coming. Here I'm talking only limited to Himalaya. I've taken a sub-regional scale, but there are various scales where you will see that climate change is all across the world in the global scale, regional scale, sub-regional, regional scale also. So I will not be talking anything which is unusual. I'm told that this is the first Earth Science talk is there, and I'm thinking there will be a certain disconnect. So I chose to speak only the very relevant portion out of the Himalaya, which can be in the Western Ghats. In Bangalore, I know there is a lot of traffic jam is there. When I travel from my earlier days in IIC, and when I go now, 30 years later. There is a lot of Tata Institute and a lot of channel is happening. The airport was moved out, which was earlier here. Why these problems are happening in particular in the need of the livelihood or increased livelihood, and that's what I am highlighting particularly over the Himalayan region. What's happening and what are the changes happening? Water is a very, very important now. If you today you look in the environment, all the newspaper must be flooded with the environmental news. So environment awareness has become very well to the at least society, but environmental awareness is not yet coming to action as of now. It is very, very less action is coming. Somebody please pull the time for me. Yeah. So Himalaya is the very youngest mountain, and it is called water tower also. And water tower means it has a reserved glacier. It has a permafrost there. We are doing permafrost research first time. It is a solid ice rock. It is a permeability plus when it freeze thaw cycle happens, you have a permafrost behavior. So water tower we call it. All the 8 nations surrounding the Himalayas pumped through this water from this Himalayan massif. There's a beautiful protruding massif outside the Himalaya. We have a doyen of the Himalaya, late Professor Waldia. They have a lot of theory on Himalaya, structural and dynamical theories. I will just try to look at the coupling of the Himalaya when it protruded out the atmosphere, right? And then there are several consistently warming episodes are coming, and then when there is a warming episodes are coming, you will see that how this warming which otherwise would not have been possible, how this warming is impacting, and then precipitation, which is a very complex kind of phenomena, and that's precipitation, how it is kind of evolving, and based on this precipitation phenomena, how we are trying to comprehend if this precipitation switch, I'll come to the precipitation switches now. Like yesterday it was thunder here, it was raining here. If you go back to the monsoonal dynamics, monsoon when it enters from the western ghats, and then when it crosses the western ghat, comes over the east leeward side of the western ghats, you have a different kind of mechanism happening. But now recently we are having, we call it a dancing rain episodes, because monsoon drops here certain rain, drops there certain rain, and we will discuss about that a bit. And then what are the evaluation in Himalayan region. So what I am trying to link, most probably, if you have most of you physicists must be have done the chaos theory, it's a very notching is there. And the Lawrence was basically the meteorologist who brought the chaos theory in 69 or 79. In chaos also, after first order, there is certain kind of order comes, right? Initially it's in just disorder, but if you calculate the Lyapunov, you will see there is a orderly comes. So this complexity I am bringing in your knowledge. This is the Himalaya, right? Beautiful Himalaya. It started coming to build up roughly 55 million year back, right? When the continent started drifting northward in the viscoplastic manner, right? And it hit the Eurasian plate, and you see that Himalayan origin came, and this origin was not very smooth, right? It was having a lot of fighting among each other. And if anybody you go get chance to move Ladakh, you will once go to this Indus origin side, you will see very distinctly suture zone where you can distinctly see the Karakoram side of the Eurasian plate, and you can see the Indian plates, and in between you have Indus flowing, and beautiful geological structure are very much visible at the suture zone, right, where these two plates are still evolving, and there used to be ocean. I'm not going on those detail of the Ladakh Gabbro and all those sediments. So when Himalaya came 55 years back, orogeny started, and that time the monsoon, which is likely to arrive now, there was no monsoon. So northward propagating air was moving towards higher plains. It was not stopped, but when Himalaya started growing up and up and up, it started stopping the northward propagating winds. And that's where our Indian summer monsoon, we call it now, it came roughly, as of the latest studies, 22 million years back, right? The monsoon started. This Himalaya started stopping this northward propagating winds, which are moist laden from the down south Arabian bodies, Arabian Ocean, Indian Ocean, or Bay of Bengal. And that's where monsoon started. And when the monsoon started, it started hitting the Himalaya, and it started scrapping the sediments, physical weathering of the sediment, and that's what is the Shivalik hills got developed. Shivalik is in general not continental Himalaya, continental mountain. It is mostly the sediment mountain, which is taken by this. And that feature, when it started coming, there have a lot of faults and everything has come. Coming back to my talk here, first three panels, if you look at that, we have a very paucity of data over this region because you are running 4,000 meters, 6,000 meters, 7,000 meters, and hence we have the gridded analysis done by various centers across the world where all the data collected across the globe goes dumped, and these centers kind of churn these data and bring those in situ observation here and there to the gridded analysis, and that's what is the observational analysis. Now the question comes that observational reanalysis itself have a lot of uncertainty. If you look at these three, how you pull this pointer, how you use this pointer. Okay, no, cursor is not working, that's why. Anyway, so if you look at these three, this is the cursor, right? No, this one. Okay. So if you look at these three, you will find that is the precipitation average over 30 years, June, July, August, September, right? And this precipitation that you are seeing here, you are finding that all the three observational analysis are generated from the same set of data, same set of observation, but still there is a lot of uncertainty among these three in the observational analysis. One is from Climate Research Unit East Anglia, one is from Aphrodite from Japan researcher, and another is for GPCC. So I just chose to pick it up to show that within the observation also we have uncertainty, right? You see northeast region, we have more amount of precipitation, you can see. So overall, a understanding is there that at least we agree that northeast region receives more precipitation. Apart from the spatial distribution and temporal distribution also, and more interestingly, if you look at the vertical elevation distribution of the precipitation in last 30 years, okay, 0 to 7,000 meter along these grid points are given in this bar here. We find that at the lower elevation of the Himalaya, right, which is from 0 to 1,000 meter, the precipitation is scattered. More variability in precipitation received at the lower elevation is seen there, right? But as you climb up in the higher regions, we have almost clustered, less variability in precipitation amount is seen, millimeter per day. So one is clear that precipitation driving mechanism, which I'll be talking a bit later, it starts struggling as monsoon, it starts climbing the flow. So at the lower elevation, there is an interaction of orography starts, which is kind of resisting or agreeing or not so agreeing, and hence you have a lot of variability in precipitation forming mechanism, and hence you have a variability in precipitation amount in millimeter per day, which is having almost lot. But as it climbs up, if it had a desire or it still has the energetics to move in higher elevations, you have more organized set of precipitation are happening. Interestingly, if you are knowing that global warming debate, people are talking that temperature are rising, temperature are decreasing. If you look at this blue line in particular and the variability spread of the precipitation of the last 30, 40 years, in the lower elevation, precipitation is likely to decrease now. Okay, and as you climb up with the blue line, we are finding that the precipitation over lower elevation is decreasing, whereas in the higher elevation, precipitation is likely to increase. All of we use, no? At home, we use sponge to wash utensil, right? So you just consider a sponge here, and it is filled with water, right? Soaked with water, and you pinch at one point. What happens? All the water start trickling down from there. Horizontally, it moves there inside and trickling out at that point there, and you have a 1 point precipitation happening in this sponge. So earlier, it was not the case in atmosphere. The sponge, if you consider the atmosphere was trickling everywhere almost homogeneously, and this water holding was distributed everywhere similarly, right? But in recent time, what's happening? The energetics of the atmosphere is happening in such a way that water is suddenly bursting out at one place, not spreading out, and that's why we have a lot of extremes, we are calling it. I have few simulation of extremes done for that purpose, which I'll share the dynamics, whatever with the certain uncertainty we could capture these, like Mumbai rain, you have a Chennai rain, you have many rains, and that's why this precipitation happening at one place. and not spread homogeneously. So the amount remains similar. Overall amounts remain similar, but this amount is, there are mouses here, right? Yeah. So the amount is kind of similar. That's what is we are finding, but the moderate and extreme events are happening more and more, and that's what is likely in the future, because the available energetics in the atmosphere, again I'm troposphere, energetics in the atmosphere is more available for such kind of activities, where your dynamical diabatic heating and precipitation forming mechanism is leading to that. Here I'm showing again the observational analysis for temperature only. Temperature is very deceptive. Actually, temperature you can sense, right? Precipitation you cannot sense, you can only visualize. So when you're warm day, you can sense you are having more temperature. But this temperature at 2 meter temperature, we consider in the atmospheric science generally, 2 meter temperature, it is very deceptive in a convective processes. Like if I give you a chance to tell that you have to make daily tea and only pour the leaves when temperature is 26 degrees centigrade. It's very, very deceptive daily if you measure that. That's what happens in the Indian Ocean and Arabian Ocean when the convection will start. Then this convection is not the physics one. Of course, it is very similar. But when I say in atmospheric science convection, it is due to the heat. Your flux is going vertically up. Evaporation and convection. That convection is slightly tweaked in the atmospheric science, and horizontal movement flux is called advection. So at which temperature convection starts, that is the reason that most of the time we face problem in the atmospheric science. And very often people are laugh at IMD or meteorological department, oh, you cannot forecast, whereas in US and UK forecast is very, very correct, because they are not suffering for convective phenomena. They are the air frontal phenomena, right? So convection is not there. Their air mass interaction is there. So the variability is in the convective phenomena to capture in the forecast model becomes very, very difficult, that at which time the energetics of the Indian Ocean and kind of a dynamics in Indian summer monsoon, which we see in last 10 years, that each year monsoon is becoming so difficult to predict because of this kind of phenomena, because Indian Ocean temperature, sea surface temperature is increasing now. So oceanic temperature are increasing. Anyway, coming back to Himalaya, sorry, I got away from somewhere to somewhere. So this is the temperature. Here also you will see different season. There is a seasonality. Also, different seasons have different kind of temperature averages, and within the observation they are having very different. And if you look at this blue curve, as we climb up here, we have the decrease of temperature. We call it lapse rate from troposphere in surface to the top. When we are going, temperature decreases, it's not increases because we are going closer to sun. No, this doesn't happen, because we have an envelope of the gases here. On top of this, these gases interact with the incoming solar radiation. Simultaneously they interact with the outgoing solar radiation. So if you have more gases surrounding over the atmosphere, we have a problem of the long wave radiation which is emitted from the Earth's surface, because it is T to the power 4. If you remember Stephen Boltzmann law, right? So if your temperature is going, so that is more concerned, that long wave radiation which is going from the Earth's surface as a black body, it warms because of incoming solar radiation. When it goes back, this envelope stops this to going to free space and radiates back, redistributes, and so on and so forth. So that is a concern here. So temperature decreases. So it is also a very deceptive phase of temperature to capture a model. So what we did in the International World Climate Research Program, let's run a regional climate model. Now, I told you observations. Now, these things we want to see in mathematical equation, which are very simple. All of you know conservation of mass, conservation of momentum, conservation of energy. These are the fundamental conservation law. And based on this, we have a 6 primitive set equations, right? And we kind of churn it in time and iterate with time, and that's what is the basic set of equations which run. Now the problem comes, we don't have all the amount available, and then mathematically we have to truncate certain of the equation to, so the exact solution sometimes is not available. So we parameterize these equations, we truncate the equation for a solution. So everywhere in the world, this is the reason for South Asian region, which is here highlighted. Everywhere the world people run for their domain, and this we did at 40 degree by 40 degree one grid, right? So we should have a resolution good. We have a x delta y. We should as minimal as possible with certain certainty, and then with time also, because we want to talk in the future 2100 global warming. So first we will again debate observational analysis, is this good, this bad, model in the present time, is this good, this bad. I'm not going in paleo, right? This good and this bad, and with this good and this bad, we want to talk what's going to happen in the future of next decade or next to next decade, right? So based on this, if you look at the this first graph, it is for maybe some of the physics boys. I'll be happy to work in chaos theory for monsoon dynamics, right? It's so if you peak, if you're looking, it's a JJS peak. That's where you get most amount of precipitation, right? But in time, we forget to have a spring precipitation, pre-monsoon, we call it pre-monsoon shower, thunder shower in certain region. Nor if somebody is from northeast, we have a Karvaisakis or nor'westers, so you have a thunder showers in Uttarakhand region. So this is the way precipitation annual cycle seems, looks like. And most of the time when we compare with, these are the model I told, we have 11 models just now, and I am comparing this with the observation, which out of those three I have chosen the Aphrodite, and with that we have taken, right, and we are comparing how good and bad model is. So wet bias, all the models are wet, they show more amount of precipitation in the model environment that than the our natural Aphrodite. And how it is distributed, if you look at spatially, this blue is the observation, I picked up one, and then these are the 9 models. If you look at the brown, they are the dry, and when you have a green, they are more precipitation. So I'm just subtracting. I'm taking the model precipitation and I'm subtracting observation, and based on that we call it bias. Okay, so somewhere model shows higher precipitation, somewhere model shows lower precipitation. Naturally you will see the lower elevation where fight is going on for precipitation in the model also. That is a very critical issue. So capturing the precipitation in the foothills of Himalaya, it becomes almost a very, very critical problem. Not only foothills of Himalaya, even if you take the Western Ghats, from where monsoon is entering and climbing up, right? That's where you have always a problem of Konkan region to predict right amount of precipitation for a kind of a flooding, for a kind of a hydropower, or so and so for social. So this is a very critical reason where orographic forcing play a very, very dominant role. We have a vorticity to look at this, and then correction also. So dry bias in the foothill, overestimation at the higher is seen here. In case of temporal distribution, we don't have any kind of trend. If I try to look at distribution month wise, we don't find any kind of distribution in this. And however, when I'm talking and comparing with the corresponding models with the altitudinal distribution, distinctly we saw that in the lower elevation you have a kind of larger variability captured in the models. Higher elevation, we have a very good cluster over the region. The most critical threshold is 3500 meter, right? Yeah.
Knowing about the models themselves,
Yeah.
in the sense that when we say climate change or and so on, so we bring in human factors, the kind of things that we are doing in order to affect the climate, which affect the climate. So how much of that is included in the models, and also the time scale? I mean, humans have been doing or have been affecting climate for only for the last 300 to 400 years, probably, not more than that. So this is a very short time scale, first of all. The second question is the 40 degree by 40 degree area that you are looking at, that is definitely spatially connected and temporally connected to the other regions of the earth. So when you are doing a model and doing a temporal analysis, for example, it would be valid only for a certain time period, because after that time period, the other regions of the earth will start affecting that particular region, right? So what is that time scale also that?
So I slice your query into one. One is the human interactions, right? We force model after 2005 with the emissions. I'll come to that when I talk the future. So we have a four regional representative concentration pathways are 440 watt, and like the pessimistic when we are adding all 850 watt per meter square carbon emissions to the atmosphere.
Okay.
That so after 2005 we have a four types of emission. One is the very optimistic that you have a minimal, everybody is doing minimal contribution of carbon emissions. So that is 260. So how the model with these emissions run in the four scenario in the future. So and then we say that if you have a worst kind of emission, that's going to be warming. If you have a optimistic like business usual scenario, which is always debated in IPCC by various government, that this much is acceptable to limit to 1.5 degree or 2.5 degree. So that's what I'll come to that. Number one, so we force these models to know the future actually, and that all gambit is done because to how to do in future. Now coming to your spatial domain and time domain, generally in a climate, what we do, we run this model almost 130 years as of now. And now we are doing another experiment where we are going, it is to 11 kilometer by 11 kilometer, because 40 kilometer is too coarse to interpret for a regional, sub-seasonal scale phenomena or sub-regional scale phenomena also, like if I'm talking of extreme. 40 kilometer or 40 kilometers too huge for an extreme to capture. Yeah. So this is for a climatic philosophy of phenomena. So we are doing that, and simultaneously temporally, which you are talking in a paleoclimate scale, which is not bothered about what's happening in day-to-day scale, which is more bothered about what's happening in 100-year scale. And so it's kind of a, you are looking at the mean value, U bar or something like that, and it is something like you want to see U prime. If you are interested in U prime, then you have to run it at much finer scale. So you need to have more computational hour, you need to have more money rather, I would say directly.
You mean the derivative?
Yeah, no, yeah, derivative, of course. If you are looking at the air pollution studies. So I'm not concerned of the mean climate.
Yeah.
Right? I'm only concerned of the U prime, that number. I'm telling it you, it can be any. Yeah. If you are talking of mean, then we are more concerned of what's happening in the 30 years average, not day-to-day average. So I'm looking for the mean character of the, like here. But I'll come to the extreme, where I'm concerned only U prime. Yeah. So that is also captured for different peaking within the model. So this model is only for climate purpose. So people are more concerned what's happened in 30-year average. 30-year average is taken primarily to avoid two solar cycles. So influence of solar cycle is not considered because there is 11-year cycle and another is 22-year cycle. So conventionally, whenever in climate I say, climate is like 30 years average of temperature at this room. So I have daily temperature of 30 years. I'll say average of this temperature for 30 years is this much for Bangalore. And above it goes 30 years, I'll say this is a warm day. If it is go below it, anomaly, so we'll say cold day. So that is the way climate, whereas weather is instantaneous measure. What is the right now weather? So very oftenly, if you talk of precipitation, maybe yesterday, if you take average of the 6th of June, maybe in the past 6th of June have not precipitated. So you can say 6 June 2022, you have a precipitation here. And that's why if recent time, we found very many one-day records are getting broken. Right? In March, we have a heat wave in the northern Indian region. But last year, March was the coldest month on average, and even wettest also. So this is a very peculiar kind of situation in extremes when people are talking. We'll discuss briefly once that. So this is what, but here in Himalaya, we have a kind of 3,500 meters is a very critical threshold. What's happening at 35, it is variability is there, like, but when it climbs 3,500 meters, something the dynamics getting changed. We don't know. We try to do it, but still we need to look at. We did a lot of statistical analysis, and we also see what is the good model out of 11, what is the bad model out of 11, and then we pick up the good model only, which gives the closest. Good model doesn't mean this will be good model for all other kind of simulation. For this particular case of Indian summer monsoon, this particular model of SMHI Switzerland Meteorological Hydrological Institute is the good model for us. For if you run for winter monsoon, it will be may not be good, right? So the modeling dynamics of this particular model, equations of this particular model suits summer monsoon very well within the dynamics, and it comes very closer. Now, if you look at the temporal correlation, I think what he wanted to ask, it's kind of a not very well always when you are talking on a time scale or when you are talking in a spatial scale. So if you are talking at one particular point, earlier I gave you a average picture of whole Himalaya. So many goods and many bads has matched with each other. But when you are talking of the individual point, and if you look at the temporal correlation, you will find that everything doesn't certain at the kind of a cube everywhere it's correct, somewhere it's correct, somewhere it's absolutely not correct. And if you look at the scatter plot here, if you see critically observation in the x-axis, model in the y-axis, so lower intensities millimeter per day are very well captured in the model physics. But if you go to the higher order of per day precipitation, it is not captured in. That's where is the extremes comes in. So we are talking extreme in a way, if statistically you are talking, it's something like outlier, right, which is beyond mean plus minus 3 standard deviation. It goes beyond that, and that's where we have to look at very specifically in these cases what's happening, these extremes, why these extremes are not being able to well captured in the dynamical model, whereas the lower intensity event will be are captured very well. I hope I'm not getting boring, all our physicists. Maybe you might be thinking what I'm talking, so I tried to make this talk very general. So yeah.
General phenomenon in the sense, if we take any phenomenon, the prediction of extremes is always very difficult, right? I mean,
Yeah.
whether it is earthquakes or whether it is stock market, whatever it is,
Yeah.
the prediction of. So, are you saying exactly the same thing here, that your models also capture the mean variability, but when it comes to extremes, the prediction becomes extremely difficult?
Yes. Yeah. So that's what we are telling. And then I will also add on that, if it is so, if it is known like that, so if the extreme happens, then what is the remedy for it? For societal benefit, actually. It is known, and we are also trying in last 10, 20 years this extreme value. So we are giving concept of early warning system. At least your model is telling extreme or not capturing.
Yeah.
But extreme happened here. Now, suppose. So how quickly this extreme early warning we can give to the society? That new, we are trying to work on that now. If there is a kind of a flood has come in higher reaches, but we do not have a good amount of prediction model for that flood or that associated precipitation. So once it occurred over there, so what kind of information we are trying to give early to the downstream society or downstream village or downstream kind of thing, right? So that's what we are trying to work, like in ISG. That's what I've started. There are certain kind of radiation of ionosphere which are captured in the tsunami. Now, tsunami we cannot predict, suppose, right? But if tsunami has occurred, now how fast this tsunami signature are captured in ionospheric signatures, which in early warning system can be percolated and can be sent forward for a forecast agency or forecast. So something like that integral debate has come for extremes if this is likely to happen. Yeah, please.
One more thing. So when you talk about taking the account of the extremes, so is that something a probabilistic model with the rest of the researchers focus on, or is it again they try to incorporate in the time series only?
In case of extreme, still there is what my kind of understanding is that the agreement is there that extremes are happening. You may be seeing the Tata Institute is ISC is doing the Vicha Center. So extreme, we are working that we have understood that there is likely to have an extremes. Now the point is how to predict it. That's the that bullseye precipitation on the map of India. Bullseye at one point is doing. That is becoming a critical issue, that how we are able to bring it, because that cannot be captured in this model, because we cannot run model at 10-meter by 10-meter resolution. Is very difficult. And where their 10-meter by 10-meter grid will be, we don't know. It can be here, it can be here, it can be anywhere. So that is the one biggest problem. So the point is that statistically people are trying, they use a statistical dynamical model, and they try to have that threshold calculated, plus minus standard deviation and then outlier, and then they try to work. But ultimately the general consensus is happening that we have to depend on early warning system, because extreme is becoming such a phenomena. Its dynamics is defined, but that dynamics to capture in this predictive sense is becoming difficult as far as the forecast or prediction is concerned. So that is the one is people are doing. And in case of temperature, I was talking on the model of the temperature. Now, in case of we find here in this temperature, higher elevation is colder in the model. Lower elevation is warmer. So this is a warm bias and cold bias. So lower elevation are in the model shows that they are warmer, and so that's is the reason. If you remember, I said that temperature precipitation variability in the lower elevation is entirely different than the higher elevation. It means that at the lower elevation you have more temperature to pump this moisture laden air to the higher elevation, but as it goes to higher elevation at 3500 meter and beyond, there is the colder temperature. So when it's a cold temperature, it is something like you have more stable atmosphere. I'm not talking LIE, okay, where temperature was also low and precipitation also low. So it's not the case of little ices which had happened, but it was the case of 1800 where Thames was frozen and everything was frozen, right? Where temperature suddenly got down and all London river froze like that, and even Himalaya also it has come. So that also we have seen, and if you look specifically this graph, most of the model March, annual March from January till December is likely to be colder in the model. So model's environment is much colder than the natural environment, and hence that is reflected in their altitudinal distribution of biases when it is going. So it has a very impact oriented issues on the environment if you look at like that, right? How the changes which are captured in last 30 years in the model, if that remains persisting for long, how they will impact to the water, how they will impact to the cryosphere, and so on and so forth. So what you are asking me about this mean and U prime, you look at that bar of black, that is my actual mean state of temperature of this 30 years. And that is the spread here. If you look at the Gaussian distribution of the model uncertainty. So somewhere we find that mean is captured, but spread is not captured. Somewhere we find spread is captured, but mean distribution is not captured in this. And most of the model is colder, and hence you can see that they are switching to the left. Now I come back to their question. Now I know this drift from observation mean, how much it is switching here. If I correct this, or if I go ahead with minus this value, and if I shift it here with this kind of correction, people are trying to work on this dynamical model output, because this is available in future also. So with this correction, they generate a kind of a statistical indices. Based on this statistical indices, they are regenerating the spatial map on which they are showing the extremes. So that's possible. So they are doing it, but still it has to need a certain kind of robustness and reduced uncertainty of dynamical model, because this uncertainty and this error will again move further and further if we don't correct it at this stage, right? So what is climate change? In general, let me tell you, there are three kind of people in climate change, right? Indian Institute of Tropical Meteorology also has done one study, and it has found that 80% of researchers don't speak about climate who are working on the climate. They don't propagate. They just work and go home or whatever. I don't comment. So the most of these 20% people of who come in the TV channel or news channel, they are not hardcore climate researchers who understand this that well, right? So they tweak their understanding as per their agenda. So very oftenly you will never find any hardcore climate researcher sitting in the panel. You will not find. They must be either a journalist, they must be a kind of common activist, and so that's what a very good study has come just 3 months back. It is done by IITM Pune. That what's the problem? It was asked. Then we found that 80% researchers, they are either shy, they don't want to comment, or they want to tell, oh, okay, you read my paper, it's fine, like it's written there. So that's kind of a very time has come that natural scientists basic scientist has to sit with the social scientist, natural scientist, right? Otherwise, that bridging will not happen if at all. If we have a transnational research to go to the societal research, policy research, nations need research. So that's very, very imperatively that we should discuss that what are the issues. Like in Ladakh, we are running Apprentice Basin network. We found that as soon as I go beyond certain region, I don't have any data. Industry is there. If temperature is rising, I'll briefly tell you, and then what is the happening over this region. So if you come to this particular site, it's a very, very interesting one, and it has an impact and relevance in the sense that if this brown color, now I'm talking the future. After knowing my model, observation uncertainty, model weaknesses, goodnesses, I'm now went to future. Now future, I don't have any observation to compare. I'm just taking this 30 years base period, 1970 till 2005, what's happening. And then based on that base period, I'm calculating, subtracting, I'm telling wherever there is a brown color you find here, that's the reason monsoon will have deficit amount of precipitation. And if wherever you have a green in the individual model, you have a more amount of monsoon precipitation in those 4 months of 30 years. Let's come to this slide, which is ensemble here. We see distinctly there is a brown ensemble means I just average all the model output. So good and bad cancel.
One question. These 9 panels are 9 different models?
Yes, yes.
And what is the essential difference between these models?
They have a different parameterization scheme, different convection scheme, different truncation scheme within that, and there are some tweaking within that coefficient within this. So these different model has something good in certain manner. That's what I have shown in the beginning one listing. So we picked up this model after doing certain benchmark check. They are coming closer. So we said, let's pick these better ones, and out of these better ones, we use what's happening. And this last panel, I have averaged all these and I found this ensemble picture where it shows that, and that is the reason you will find that this Cherrapunji rainfall has shifted to Mosinram. Right. So in another finding, what we find, if you look at the Indian map and if you look at the monsoonal flow is shifting westward. And likely in the future, what we have shown in that study, that Rajasthan is going to be more greener now. So we kind of concluded that beginning of our at last conclusion that it's going to happen that in monsoon when shift westward, right, you will have less amount of precipitation here. If you look at this, topographical structure, you have a Khasi Jaintia hill and you have a Himalaya is interacting. You have a cusp there. So monsoon in earlier time was having less energetics. It used to go and take time, and then this don't allow monsoon to go further. It will take turn and go foothills of Himalayas. Now monsoon itself has a lot of energetics because SST warming. So it is coming with a lot of power now. So it doesn't have time to stay there. It immediately turns by itself and then moves towards foothills of Himalayas. So it doesn't go deep in the northeast now. So it is shifting this word, and that is one of the reasons. Of course, we have not done that specific analysis of Cherrapunji and Mosinram because that is a very micrometeorological study, right? But over this shifting to western side, Gujarat, Banaskantha, Badmer, if you remember, these 10 years time, a lot of flood has come there. A lot of monsoon rain happened in the June, July, August, September, all the Rajasthan region. Sorry. Yeah.
One more thing. So this future projection that you have made is what is the time period for which this is being made?
This
because
is
the data is based on 30 years.
This must be for 2020 to 2049. 2020-2049.
So again 30 years.
Yeah, again 30 years. So we take means 30 years. That's a convention we guys are following actually. That's the problem. So 30 years we call near future, mid future, and far future is that.
But what is the confidence? I mean, do you have full confidence over the entire 30 years, or the confidence is much higher for near future, and then does it become less over the?
So far future, you have confidence started becoming lesser and lesser because model runs by its own dynamics. But near future, we have more confidence because it's here we have left it. So it was controlled here. Here it is going by itself. So as it drifts away, so we have less confidence in the.
So when you're saying that the monsoon is shifting westward, for example, the centers of the extreme events. So I mean, when you're predicting Rajasthan will become greener, for example, does it mean that it will shift all the way from here to here? Is that the prediction?
Yeah, that's what we have, and that's not prediction. That is the real-time observation we have done. This is 20. I think 2001 or 1990 to 2020. So in real time, we have shown with the data.
Okay.
So it's a real time. We saw that because of the global warming forcing, monsoon has shifted in the present, and that's what corroborates with the finding also.
Okay.
So that's what we are telling. If that happens, monsoon is likely to go more westward because monsoon has a lot of energy.
So, and that energy is coming from the climate change.
Climate change, exactly. Sea surface temperature is warming.
Right.
So climate and even your land surface are warming.
Okay.
So you have a lot of energy freely available in the atmosphere energetics. Right? Tropical cyclone is moving faster. If you follow, I'm just talking very generic, okay? So if you remember tropical cyclone, which is originating from Bay of Bengal and entering to the land in ocean, Orissa coast, Andhra coast, and so on and so forth. Earlier, if you remember that as soon as it is to nightfall and landfall, it used to die. It never used to enter so long, right? But if you remember last few tropical cyclone, it has gone entered till Jharkhand, Bihar, and not only entered, they kept getting supply of the moisture because there is lot of available in the tropical cyclone SOP now. Lot of energetics is applied, so it is keeping the tropical cyclone alive. Not only it is keeping the tropical cyclone alive, it is supplying all the moisture also. So now if you see the latest 5 years tropical cyclone, they intruded much inside than Orissa and came up to Jharkhand and Bihar also. And simultaneously, you have more tropical cyclones in the Arabian Sea side also, which otherwise is less because Arabian Sea is saline than the Bay of Bengal, because Bay of Bengal get a lot of fresh water from northern rivers than Arabian Sea. So Arabian Sea is also having now tropical cyclone because energy is so much. There is any initial perturbations is coming. Instability, baroclinic instability comes in the atmosphere. It kind of grows in the free atmosphere and kind of thing, right? And that's what you, if you look at the 1970 till the precipitation 2100, this graph, we find a lot of changes happening, a lot of uncertainty are happening, and the question which you asked, how different emission, we call it RCP. If you look at the 2.6, this is 260 watt per meter square if everyone thinks added in the free atmosphere, and similarly 450, this is worst 850 watt. So everybody is emitting, and that's where we saw that elevation dependent changes how it's happening. So you will see that where 8.5 hectopascal is there is an increase uncertainty is there likely because definitely you have more amount of emission added in the free atmosphere. So yeah.
Just wanted to say we have 10 minutes remaining for the talk.
Yeah. So these are the temperature rise if you're trying to look at, right? In the above projections, these are the running 2100 in different season. And we found that in case of particularly, if you look at this graph, right, your red variability is very less. Why? Because by June, July, August, September, you have monsoon moisture has entered in the atmosphere. By virtue of the monsoon moisture in the atmosphere, your temperature is dampened. That's why you don't have a higher temperature in monsoon months, only March, April, May, because they are dry months. So moisture is not available. So in free atmosphere, moisture and temperature play a kind of conjugative role. You cannot separate them. They play each other, they hold each other. And if you have more temperature, more evaporation, if moisture is there, temperature is kept down. So they are having very integrated role happening here. And that's where we try to put at the winter warming elevation dependency in this graph. If you look carefully, you will find at 3500 meter elevation, you have a distinct change happens. Below that threshold, you have a very different kind of things, and above that threshold, you have a very different kind of things are happening over this. These are the various soil moisture, down welling, long wave radiation, so many factors we have seen here, and we found that at that elevation in particular, and if that happens, impact will be immense. Your snow line will come down, your vegetation line will come down. If that happens, your animal migration of species will come down. That's what we are seeing in the Himalayan belt. Species are taking over, pine is taking over oak. If oak is come, its micrometeorology is very different. It is a moisture soaking plant, whereas pine is not moisture. So if that happens in due course of time, where species, animal species migration, plant species migration, or maybe in due course of time, habitat migration will happen, and that's what is the reason we read Harappa Mohenjo-daro, because they died because of the famine, because of the droughts. And not only that, now with climate change, terms of climate crisis, climate migration, there is a report that Mumbai certain part will be going down. So these migration will come, and if this geo migration will come, it may goes to many directions. I'll not go into those details right now. Coming to Karakoram anomaly, one reason of specific reason in Himalaya is that your Karakoram glaciers are growing. So that's why it is called anomaly, whereas rest of the glacier are dying. So we try to look at this work that why Karakoram glaciers are still growing, right? What's happening now because of this increased moisture? If you look this blue color, and this lifting condensation level is where nowadays you will look more of the cloud. No, if you look outside, you will have a cloud base. So when moisture parcel is climbing up and it finds a complete saturation, you will have cloud starts building up. I'm not going in cloud microphysics. And then when it goes top, where is the LFC, level of free convection? In between this cloud will make, right? So when a lot of moisture is going over that region, this is the cold desert. If you go Ladakh, you will see beautiful Ladakh. You will say this is the cold desert there. But now what's happening, that a lot of moisture is going, and the Karakoram is sitting at the lifting condensation level. So when it is lifting condensation level, it is getting a lot of mass to grow, which is not the case at other glaciers because they are at the lower elevation. So Karakoram Glacier, there are many glaciers. Elevation is interacting with the lifting condensation level of the clouds. So it has a lot of replenishment is coming now. So such glacier which in Himalaya at that elevation and at the present time of change, it is showing that those glaciers are increasing. Yeah. And based on that, we gave a hypothesis because I don't have an observation. So I called it hypothesis because I did this based on the model data only. So once data in future is available, and since it's a geopolitical conflict region, if it is available. So black thin one is Karakoram and the round one is red one is Ladakh. We have a negative trend. This, if you look, is defying the global warming. This region says the temperature is decreasing here. It's not increasing at regional scale. Why I highlighted this region? Primarily to let you know that climate change doesn't mean that everywhere temperature is increasing. At sub-regional, sub-regional scale, temperature are decreasing here. So this 30-year trend shows in the real time, in the model, the temperature is decreasing, and by virtue of this temperature is decreasing, snow amount which is supposed to be melted, it is growing. So if your snow amount is growing, the growth, that is the Karakoram anomaly, and hence you have a short wave and all those secondary order of derivative long wave which is coming from sun transferred back to the sun is happening. This is the Indus River Basin. It brought me into the conflict because I published this work. Some senator quoted in the Pakistan Assembly that their researcher himself is telling that ambitious project in upper riparian will affect the lower riparian. But that's what based on facts. So I got saved in that because of that. So RCP 2.6, if you are talking in the Indus one, right? First one, this is 2.6 optimistic emissions. You will find that they are different scale. So don't look at the color. Their color scales are different. In case of RCP 8.5, you have a huge warming happening over this region. If this huge warming is happening at this region, over this region, likely if you look at the graph here, right? So ultimately, unanimously, we saw in all the model, in all the emission scenario, warming is much, much higher. And if that is happening in case of precipitation, particularly, good thing in the upper riparian region is because of this warming, more amount of moisture is going over this region. If you look at the red color, it shows that trend has positive in last 130 years of the model output, right? So it shows that precipitation supplement will be keep going more in the upper riparian, but lower riparian is drying, right? Lower riparian is drying, which is present Pakistan, but our riparian is increasing this, and we have thus more amount of water storage available for us in the future, particularly in this region, right? So water is a evaporation minus condensation, so total precipitation, so that is getting reserved over this region, which may be utilized in for other purposes or some purposes also. In Kashmir Valley, if you look, I told higher elevation warming rate is there, but in the Kashmir Valley, if you go, the elevation, lower elevation is warming. Upper elevation of its periphery basin is not warming. It's reverse than the other mountainous region, right? Why it's happening? Because it's a closed valley. People burn there a lot of bukhari in winter, and otherwise also they burn a lot of food. So this emission at localized valley is getting trapped within this basin, and outer flowing atmosphere is not mixing with it. So intermixing is not happening. So it's a very internal mechanism which is letting this floor of the valley trend warming than the higher elevation, which is not the case in another Himalayan region, where we found that the temperature is warming rate is more. In this case, is reversed. Similarly, we found that Satluj, we don't have much change in precipitation. If you are coming eastward from Karakorum, Indus, and then here, but there is a likely that temperature is increasing here, but there is no change in precipitation. This is the cusp region where Indian winter monsoon comes in December, January, February. Indian winter monsoon goes in the. Similarly, in Ganga also, we found Ganga River Basin. We don't find it much region. These all inputs has gone for various purposes of the various ministries for in analysis, right? And this is the way it is the future climate projection. And briefly, I'll come to the extreme. I have nothing much to show here because there is some of the movies I brought. But one thing I would like to say that the shaded region shows that there is a 1.6% rise in the Himalaya is because happening, which is shows that the precipitation per day is 200 millimeter and above. So 200 millimeter is a huge precipitation. That's what comes in the cloud burst category, that suddenly it is coming, and one or odd cloud burst we try to capture like anything, and we have shown that yes, within 15 minutes or within the minute you have precipitation within a minute going to 60 millimeter or 120 millimeters. So that is the essence of this data. We want to show that there is a likely increase happening. And if you remember that slide, I was telling that how to capture these thing and translate into some early warning system, and that's what experiment what we did. We took one or two odd experiments where this is a peak suddenly in September happened in the Uttarakhand region, Ukhimat. There's a place, there's a lot of devastation happened, but this is a daily data. So you can see only this 200 millimeter per 24 hours, right? In this graph taken from the India Meteorological Department. But ultimately that 200 millimeter happened in how much time? Was it in 24 hours? If it is 24 hours, then it cannot do that much damage. So that's what we wanted to see how it happened. And then we saw various reflectivity, distribution of it, mixing ratio, which is hydrometeors, various hydrometeors, and we could find this bullseye here. Look at that. We find that how much mass in this has been suddenly downpoured only at that region. Rest of the shaded portion is the topography here. These are the topography, but here, and then what we told this cloudburst is a convective phenomena locked in the orography. If any one of these two processes are missing, cloudburst will not occur in Himalayas. So you have a convection perturbation. So perturbation started moving now. Now this guy, if get locked in orography somewhere, so orography pushes it up, and how it looks like along this cross section, this line cross section, I will show that evolution here. If I think, if you look at this cross section, how this is behaving, how this is moving, and suddenly it pumps, and yes, here it peaks. And if you look at the vertical cross section here, it will be very, very distinct. It not only it peaks, it goes up to that particular minutes up to the 14 kilometers height, which is very, very difficult otherwise to push a air person in 14 kilometers. Here it started becoming, and now it is going up, and this is within a fraction of minute, within a fraction of minute. And based on these, we tried to analyze with various scheme. You asked me what is the problem with model, right? So now I'm telling this, the model has a very, we run it at a delta x, delta y, and delta t. So we have one value, and as I from grid 1 to grid 2 I switch, it has a different characteristic. Now these two grid doesn't have the mass flux among them in general, most of the model, but in this Cosmo D model there is a provision of mass flux horizontal advection also, convection plus horizontal advection. That's why this particular case is captured in this model only because it is a horizontal flow of mass from one place to another place, which otherwise very static in other models. So that is the kind of a modeling strategies also people are adopting. And here you look, the precipitation within a fraction of minutes, a fraction of seconds are happening. This is 122 minutes slide we had trying to put, and you have a detailed precipitation distribution over this. Another is a Ladakh cloudburst. It happened 2010. We tried to analyze also if you look at this, but still we are unable to capture the reason, though it's published. But still I have a question, from where this much amount of water came in Ladakh? I could not answer it actually with my kind of understanding of geomorphology of Ladakh. When I look at Ladakh, and for cloudburst, you should have a lot of amount available for precipitation. So that's what I could not answer based on the model as well as the observation also. Here is the maximum reflectivity. Interaction of orographic is clearly seen here. This is orography, and you can see that cloudburst is distinctly seen here, and that is the measure given to NHPC Chile when the storm has come, and based on that they have calculated the storm flow also. And these are the few conclusions that intermodal disagreement is there, as you rightly said. Precipitation and warming rate are integratedly together with each other. Downwelling long wave radiation as well as the energy, I would rather say energy in a composite manner, that this energy is driving mechanism over the Himalayan region. Particularly it becomes more complex because we are not talking of the horizontal plane, we are talking of the variable orography, and not only variable orography topography, we are also talking about heterogeneous land use land cover. Somewhere you have a plant, so your land use land flux coupling, Bowen ratio, or maybe other Butko curve, they will have a very different interaction and infusion in the model. And based on this, we have to improve upon a lot of the things in the model. So thank you very much. Okay, this is a one brief I started once I moved to IIG, how the solar wave versus heat wave is happening. If you remember the media, they have declared solar wave roughly from ISER, Kolkata, Professor Devanandu Nandi or somebody. It came in that the solar flare were there in a few weeks back than this. And we found kind of a distinct relation. If you look at 28th, 2020, these dots are stations, Indian meteorological stations, and temperature are above 5 degree normal for quite some time. So we are trying to look, there is a signature of solar flare over this increase. Yeah, that's it, I think. Thank you very much for patience listening. Thank you.
Thank you.
One
Yeah,
previous question before we,
Yeah.
so I would like to know, like a lot of the mountaineers who go to Himalayas, they drop their baggage or the garbage there. Does that also affect the overall climate change and precipitation in Himalayas?
Well, of course, garbage issue is slightly different than the dynamical issue, but yes, from environmental point of view, that's a very critical issue, particularly when you are talking of a very sub-regional scale. Like we are talking of the springs, spring water are drying. So these are choking the local spring in the hydrological cycle, because most of the Himalayan region, Uttarakhand region, Northeast region, there used to be the natural spring water, right? We found that in the spring geothermal cycle, these are kind of holding these springs, and that's why springs are drying, because within the earth also there is a kind of channel happening, and these are going further down. One second thing, if you are looking for the interaction of the coupled interaction at the regional scale, definitely that is also we have seen in environment. So that's why these are the landslide. I didn't bring many of the issues. Landslides are more prominent because of that, because the local anchorage, which landslide will happen as your things will get drier, vegetation anchorage for the landslide in Himalayan region will be happening like that. Yes. Okay.
So
Anybody?
one more question was,
Yeah, please.
the human factor that is incorporated in these models, is it only through that RCP factor that you were saying?
See, these models are configured based on the general consensus by our intergovernmental panel of climate change, right? Wherever all the in that generally people talk of the carbon emissions to be suppressed, because, and by virtue of suppressing minimal carbon emission, your warming will be minimal. So yes, you are absolutely right. In one way, that is the only intervention in dynamical model is considered. But there are a prototype separate kind of studies where uh, his viewpoint or other viewpoint on the regional scale model or the local scale, these can be have multifaceted, multi-factor models to project. That's happening also, because these are for a general global platform, World Climate Research Program. But yes, at regional scale, even in the Indian scale, various factors like in Upper Indus Basin, we are having questionnaire model. We talk to individual people, individual old age people, even the gender balance also we talk, right? How this gender balance, water issue we talk, because water you have to be taken from, then there is religion also, different religion look at. So these are the various efforts with social science is also going on, because they are more comprehensive to make us understand that what are the need of the societal forcings, health, water, and many other things also. Yes.
Any other question?
Okay, nothing then, yes. Okay.
Yeah.
Thank you very much
Thank
for
you,
your
Professor.
patience listening. Thank you.
Thank you so much. Thank you.